So what we have done is we have written this u of xt as u of xt as summation n equal to 1 to infinity. We have the value as 4 upon pi n cube, 1 minus 1 to the power n. The value is sin nx into e raised to minus n square t. Okay. You can even take out, if you want, you can take out here 4 by pi outside, but you can't take in this case the terms containing the value n outside, correct? So this can be the solution. If you want, you can even do it further, that taking that n equal to even and odd. If n is even, then minus 1 to the power n will be 1, and that will become 0. And if n is odd, then the value is going to be 2. So that also you can add it if you want to. Otherwise, even if you write the solution like this, still you will get the full credits for that. Okay. So this is our required solution. This is the required solution for the problem. Required solution for the problem. This is one category of example. One category of example. Let me take one more category of example here for So in some cases, you may have the function or the value of that u of x0 can be a constant value also. Whenever it is constant, it is very easy to solve the entire part. So we have another type of question where the one of the side is insulated. So that is your second category of type of problem here. So let us take that example. Solve the partial differential equation kappa u by kappa t is equal to k times kappa 2u by kappa x square for the conduction of heat along a rod without radiation subject to the following conditions. The first condition is u is not infinite. So let me tell you, sometimes it is given that u is finite, sometimes it is given that u is bounded, in some cases it is given that u is not infinite, correct, as t tends to infinity. So as t increases, u is finite, correct, or bounded. The second condition is given that dabba u by dabba x is 0 for x is equal to 0 or L. That is, here in this case, as I said earlier, that whenever the insulation is carried or there is no heat flows, here X is taking the value 0 and L. So we just claim that the plate is of length L, correct? So here at both the ends it is insulated or no heat is flowing through it. So we can write it down that the ends are insulated. Ends are insulated, that is given. The third thing is given that u of x0, u of x0 is Lx minus x square for 0 less than equal to x less than equal to L. Less than equal to x less than equal to L. Okay. So all these things are provided here. Now we have to just solve this equation. So you can see immediately that this is our one-dimensional heat flow equation. These are insulated, so I have to use this boundary condition, correct? Instead of the earlier condition. In earlier case, you have seen that u of x0 is 0 and u of x5 was 0, correct? But here partial order derivative you have to take. So first thing is you always start with a general solution. What is the general solution here? So the general solution is u of xt is equal to, we have this c4 cos mx plus c5 sin mx into e raised to minus c square m square t. Now if you just observe here, what is the value of c square given? It is given as k. Okay, it's given as k. So we'll use this value here and this can be written as, in place of c square, now put it as k. So u of xt is now becomes c4 cos mx plus c5 sin mx into e raised to, it is minus k m square t. Minus k m square t. Now we'll use the boundary condition. So they, what is given? Dabba u by dabba x is 0 for x is equal to 0. Correct? For x is equal to 0 and that is for all values of t. So now what I'll do is I just differentiate this. We'll call this as equation number 1. So differentiate this one with respect to x. Differentiate one with respect to x. So what we get this as? So dabba u by dabba x is equal to, it will be derivative of cos is sine minus sine. So I get minus c4 m times sine mx, correct? Then here we'll get c5 m times cos mx. And this e raised to minus k m square t will remain as it is because you are taking partial order derivative. Now put here x is equal to 0 and dabba u by dabba x is 0. So what we get this as? So we'll get this as c5 m times cos 0 is 1, correct? Into e raised to minus k m square t is equal to 0. You can see that m cannot be 0. If m is 0, then everything is, you can see that there is e raised to 0 is 1 and you will get a solution as c4, which is a constant value. We don't want that. So m cannot be 0. Similarly, e raised to minus k m square t is also non-zero. So what we get from this? So we'll get this as c5 is 0. So put the c5 equal to 0 in equation number 1. So put c5 equal to 0 in equation 1 and now equation 1 will get modified and you will get a modified solution now. So u of xt is what? c4 cos mx e raised to minus k m square t. We'll call this as equation number 2. We'll call this as equation number 2. Now once we get that, we have to now solve this further. So for solving this further, you have to take the next boundary condition, the way we have taken it earlier. So we'll take dabba u by dabba x is equal to 0 for x is equal to L. So that is our second condition. We'll use that condition directly, second boundary condition here. We'll differentiate this 2 with respect to x again. So we'll write it down this as dabba u by dabba x is equal to, what I have is, I have in this case this C4 cos mx. So derivative of cos is minus sin. So we'll get minus C4m. So minus C4m times sin mx, and e raised to minus k n square t will remain as it is. Now you put dabba u by dabba x is equal to 0 when x is L. Correct? So substituting that will get minus C4m sin ml e raised to minus k m square t is equal to 0. So you can see that C4 can't be 0, because if C4 is 0, the original equation will be 0 solution, which we don't want. M cannot be 0, correct? Even we have exponential term, that is also non-zero. So what is 0? We'll have sin ml is 0. Okay. When it is 0, then for which angles you will get the value of sin function as 0? So ml is equal to m pi. Correct? For n equal to 1, 2, 3, 4 and so on. So what we get here, the value of m is n pi by L. So this I have to put it in the equation. So for n equal to 1, 2 and so on. So let me substitute in the equation, which is our equation here. So the equation in this case is this earlier equation number 2. We'll put it in equation number 2. So put m equal to n pi by L in equation 2. So what we get this u of xt as? So this again the formula is modified, the solution is modified. So that is C4 cos n pi x by L. C4 cos n pi x by L. Correct? In place of m, we are putting it as n pi by L. E raised to minus k. We have here n square t. N square t. So in place of m, we are putting n pi by L. So it will be what? Minus k n square pi square upon L square times t. Correct? So this is the solution for n equal to 1, 2, 3, 4 and so on. So let me write the general solution from this. So the general solution is the summation of all this, correct? So we write it down, the general solution u of xt as summation n equal to 1 to infinity, correct? We write here an cos of n pi x by L into e raised to minus k n square pi square upon L square times t. This is the general solution. So we are just clubbing all the solutions, and that is the solution. Now we have to calculate the third one. So we have to find out now an. So what we do is we put u of x0 is equal to Lx minus x square for 0 less than equal to x less than equal to L. So let us substitute that. We'll call this as equation number 4 now, 3 now, correct? So substituting in 3, we'll get this as u of x0 is equal to what? We'll get this as summation of an times cos of n pi x by L. Now you can see that we have here cos function, cosine function in the series. So we are going to take the half range cosine series. That is the only change. Okay. So what we do is we'll represent this by using half range Fourier cosine series. So representing it by taking half range Fourier cosine series, correct? So this can be written as an. The formula of an is what it is, 2 pi L. L in this case is L in this case, correct? Small l, 0 to L, correct? We have the function as Lx minus x square, and here it will be what? Cos of n pi x by L, correct? The angle which we have it here, times dx. But you know that for cosine series, the 0th position values also exist, that is a0. So I have to calculate even the value of a0. So what is a0? A0 is going to be 1 upon L integral 0 to L fx dx, correct? So fx is what? Lx minus x square. dx. So solve this. So what we get this as? So this is 1 over L. Integral of this is nothing but L times x square by 2 minus x cube by 3, and this is from 0 to L. So when we put it here, so we'll get this as L cube upon 2 minus L cube upon 3. So L cube, I'll take it out. So this will be what? L square. And here we get 3 minus 2. So L square minus L square by 6. This is the value of A0. So A0 in this case is what? It is going to be L square by 6. This you have to calculate. In sine function, we don't have to calculate that because sine value is 0, correct? But A0 cannot be 0. So that specially we have to calculate in this case. Now you apply again integration by parts generalized rule. So take this as u and v and calculate this. So it is 2 by L. I'll put it uv1. So it is Lx minus x square into integral of cos is sine of n pi x by L upon n pi by L, correct? Minus, now take the derivative of this, so it will be what? L minus 2x. Take the integral of sine, which is minus of cos n pi x by L upon n square pi square by L square, correct? Again, one more n pi by L will get added. Then next is what? Plus, we'll have it as minus 2 and take the integral of this, which is what? Minus of sine of n pi x by L, correct? Whole divided by this is n cube pi cube by L cube, and this limit will be from 0 to L. So when you put the limits here, so you'll find it out that second is what? L minus 2L. So we'll get this as minus L. So we'll get this 2 by L times, correct? We'll have it as, when I take this L square in the numerator, we'll get L cube there. So minus of L cube minus L cube upon n square pi square, and we'll have here cos of n pi L by L. So it is cos n pi only, correct? And when you put it here, so sin n pi is 0 only. So at the upper limit, you will get only middle term. And when you put the lower limit 0, sin 0 is 0. Even the third term will be 0. There is only second term exists. Cos 0 is 1. And we'll again get minus 3 times. So it is what? Plus 4 times we'll get. So it is plus. And we'll have it as this as L square. Correct? L square. And here it is cos 0. So it is L cube again. L cube upon n square pi square into 1. So we'll get this term. So again, I'll take out here the common term outside. So we have 2 times. So this L cube, when you take outside, divided by outside, one more L is there. So we'll have it as 2L square, correct? Upon n square pi square into 1 minus cos n pi. So this is the value of an. So once you get this an, now the part is very easy to write. You have to write it down the entire solution here. And so this can be written as, the solution can be written as, so I have to add that a over there, okay? So the general solution is u of xt. Let me add the value of the a0 here. A0 is what? L square by 6 plus summation n equal to 1 to infinity. We are just putting the value of, in this case, this an is 2L square by n square pi square, 2L square by n square pi square into 1 minus cos n pi. You can even put cos n pi as minus 1 to the power n. And what we have here, we have cos of n pi, correct, in the general solution into this. So cos of n pi x by L, so into cos of n pi x by L into e raised to minus k n square pi square t upon L square, correct? So this is your required solution. If you want to convert it in terms of even and odd cases, you can convert it. That is open to you. but this is the way that you have to solve it. So whenever it is insulated, so you have to use in this case half range Fourier cosine series. And whenever we have the earlier question without insulation, correct, the heat is flowing on a uniform bar, then in that case you are using the usual half range sine series formula. So in cosine series, you have to find it out the value A0 separately. That you have to remember, correct? Rest all the part is same. Here you have to just follow the sequence of the conditions given as it is. So first of all, you take the boundary conditions and next you go for t equal to 0, u of x0, and then you apply respective half range sine or cosine series, correct? So this way we are doing the heat equation, one dimensional heat flow equation.